Welcome to an introduction to higher order linear ordinary differential equations. The concepts of higher order linear ODEs are essentially the same as second order ODEs. We replace the order of 2 with the order of n. Let's begin with the general homogeneous linear equation, which is equation 2.4 shown here on the right. Notice the dependent variable is y. The coefficient functions are p sub n minus 1 through p sub 0, and the differential equation has order n. Notice the first term, we have y with an n in parentheses in the exponent position. This represents the nth derivative of y. Notice in the next term we have the n minus 1th derivative of y, and so on all the way down to y prime and then y. And now let's talk about superposition. Suppose y sub 1, y sub 2 through y sub n are solutions of the homogeneous equation 2.4, again the equation shown above. Then y equals c sub 1 times y sub 1 plus c sub 2 times y sub 2, all the way down to plus c sub n times y sub n, also solves the differential equation for arbitrary constants c sub 1, c sub 2 through c sub n. In other words, a linear combination of solutions to the differential equation 2.4 is also a solution. We also had the existence and uniqueness theorem for non-homogeneous linear equations, where suppose that p sub 0 through p sub n, the coefficient functions, and f, the function on the right, are continuous functions on some interval I. A is some number in the interval I, and b sub 0 through b sub n minus 1 are constants. Then the non-homogeneous nth order linear ODE has exactly one solution, y of x, defined on the same interval I, satisfying the given initial conditions. Notice how for the nth order differential equation we have n initial conditions. And now let's talk about linear independence. When we had two functions y1 and y2, we said they were linearly independent if one was not the multiple of the other. The same idea holds for n functions. In this case, it's easier to state as follows. The functions y sub 1, y sub 2 through y sub n are linearly independent if the equation c sub 1 times y sub 1 plus c sub 2 times y sub 2 all the way down to plus c sub n times y sub n equals 0 has only the trivial solution where c sub 1 through c sub n all equal 0, where the function holds true for all x. If we can solve the equation with some constants where, for example, c sub 1 doesn't equal 0, then we can solve for y sub 1 as a linear combination of the others. If the functions are not linearly independent, then they are linearly dependent. And now let's talk about the Wronskian and how it can help us determine whether functions are linearly independent. If we are given the functions y sub 1 through y sub n, and they have at least n minus 1 derivatives, then the determinant shown below is the Wronskian. Notice the first row contains the given functions, the second row contains the first derivatives, the third row would contain the second derivatives, all the way down to the last row, where we have the n minus 1th derivatives. And again, this is called the Wronskian of the functions y sub 1 through y sub n. So if we have a set of functions y sub 1 through y sub n that solve a linear, homogeneous, nth order differential equation on an interval I, if the Wronskian of y sub 1 through y sub n doesn't equal 0 for all x in the interval I, then y sub 1 through y sub n are linearly independent on the interval. If the Wronskian of y sub 1 through y sub n equals 0 for all x in the interval I, then y sub 1 through y sub n are linearly dependent on the interval. So again, if we have the functions y sub 1 through y sub n that solve the nth order linear homogeneous differential equation on the interval I, and the Wronskian doesn't equal 0 for all x in the interval, then y sub 1 through y sub n are linearly independent, and the set of solutions is called the fundamental set of solutions, and therefore the general solution is the set of linear combinations of y sub 1 through y sub n. I also want to review what the Wronskian means when we have any set of functions y sub 1 through y sub n, meaning these functions don't necessarily solve a linear homogeneous nth order differential equation. So for any set of functions y sub 1 through y sub n that are differentiable on some interval I, if the Wronskian doesn't equal 0 for some x in the interval, then y sub 1 through y sub n are linearly independent on the interval. Notice how this is slightly different than if the functions solve a linear homogeneous nth order differential equation. For any set of functions, we have the Wronskian doesn't equal 0 for some x in the interval, and if they solve the differential equation, then it says the Wronskian doesn't equal 0 for all x in the interval. Notice there is a slight difference, but in fact, if the set of solutions does solve a linear homogeneous nth order differential equation, we can actually use either definition, because if the functions solve the differential equation, the Wronskian will always be non-zero or always be 0. And then again for the second bullet, for any set of functions y sub 1 through y sub n, if the functions are linearly dependent on the interval, then the Wronskian is equal to 0 for all x in the interval. Again, we have a slight difference here. For a set of any functions y sub 1 through y sub n, if they are linearly dependent, then the Wronskian is going to equal 0, but that doesn't mean if the Wronskian equals 0, the functions are linearly dependent. However, if the functions do solve a linear homogeneous nth order dE and the Wronskian equals 0, then we do know y sub 1 through y sub n are linearly dependent. Let's look at an example. We're asked to determine the Wronskian of y sub 1 and y sub 2. We have a 2 by 2 determinant where the first row contains the functions and the second row contains the first derivatives. The determinant is equal to 2 e to the 2x times negative 2 e to the negative 2x minus e to the negative 2x times 2 e to the 2x. Simplifying, we have negative 2 e to the 0 minus 2 e to the 0, which simplifies to negative 4. Notice how the Wronskian is always non-zero. This indicates that y sub 1 and y sub 2 are linearly independent, and if they were solutions to a second-order linear homogeneous differential equation, then the general solution would be the linear combinations of y sub 1 and y sub 2, meaning the general solution would be y of x equals c sub 1 times e to the 2x plus c sub 2 times e to the negative 2x. So now we know that if y sub 1 through y sub n are linearly independent and solve the nth order linear homogeneous differential equation, then the general solution is a set of linear combinations of y sub 1 through y sub n. These theorems give us a method for solving higher order linear homogeneous differential equations in the following form. Number 1, we find n solutions, which are y sub 1 through y sub n. Number 2, we check to see if y sub 1 through y sub n are linearly independent, and if they are, then we know the general solution. I hope you found this helpful.